This is the final part in a series of quantum physics videos. If you've missed the other videos, please go see the link in the description. In this video, we're going to observe for each particle through which slit it goes. This observation won't affect the particle in any way. To understand how we do this, we need to take another look at what the BBO crystal does when it converts the single photon into two separate photons. When the photons get converted in the crystal, they also get polarized. This process is called polarization. If you don't know what polarization is, for understanding this experiment, it's enough to know that it's a certain property of these photons, and that a photon can be X polarized or Y polarized, or left polarized or right polarized, or completely unpolarized. For now though, we're only interested in X and Y polarization, since the photons coming out of the BBO crystal are always either X or Y polarized. Of course, we don't know the polarization of the photons right when they come out of the BBO crystal. But we can measure the polarization of each photon when it arrives at the detector. So, for example, the photon going into direction A could be X polarized, and the photon in direction B could be Y polarized. Or it could be the other way around. However, due to the way the BBO crystal converts the photons, they can never be polarized the same way. For example, both photons can't be X polarized at the same time. I won't go into detail right now why this is the case. Let's just say it's the way the BBO crystal works. Now what that means is, when we measured the polarization of one photon at one of the detectors, for example, we measure photon A to be X polarized, we automatically know for sure that photon B is Y polarized. Why does this all matter? Well, now we'll introduce the key element that will help us determine through which slit each particle went. A new crystal, a so-called quarter wave plate. Now, these crystals have the property that they change the polarization of the photons when they pass through. You might be skeptical of these crystals now, but it's important to note that they only change the polarization. They do not affect the photons in any other way. Even if that doesn't convince you now, it'll be clear later in the video. We'll have two versions of this crystal. To simplify, we'll just call them a red and a green version. The red version we'll put in front of the left slit, slit 1, and the green version in front of the right slit, slit 2. Now, when a photon passes through slit 1, it also has to pass through the red crystal. And when a photon passes through slit 2, it also has to pass through the green crystal. What do these crystals actually do? Remember, we talked about the fact that the BBO crystal polarizes the photons to be X or Y polarized. These crystals also change the polarization of the incoming photons. Let's forget about the B side for a second, and let's just take a look at the A side. Let's say an incoming photon is X polarized and randomly goes through the red crystal. The red crystal is set up in a certain way so that it changes the X polarized photon to a left polarized one. So again, an X polarized photon going through the red crystal is going to be left polarized when it arrives at the detector. Now let's do the same thing with a Y polarized photon. This time it will be right polarized. So to summarize, the red crystal changes the polarization of a photon, making an X polarized photon left polarized and a Y polarized photon right polarized. Okay, now let's take a look at the green crystal in front of slit 2. This green crystal is set up so that it has exactly the opposite effect from the red crystal. let's say an incoming photon is X polarized. When it passes through the green crystal, it will be right polarized afterwards. And of course, a Y polarized photon passing through the green crystal will be left polarized. Now the thing is, we can only detect a photon's polarization at the detectors. We don't actually know the polarization of the photon right after it leaves the BBO crystal. The detector will only tell us the final polarization of the photon, which will be either left or right polarized. But as you can see from the table, that information by itself doesn't tell us through which slit the photon went. This is where the B side comes into play again. Remember how the BBO crystal always polarizes the photons in the opposite way? When one photon is X polarized, the other must be Y polarized, and the other way around. So let's say a photon arrives at the B side and the detector tells us that it is Y polarized. Now we instantly know that the A photon must have been X polarized the moment it came out of the BBO crystal, simply because that's how the BBO crystal works. Now it goes through the double slit and arrives at the A detector, and let's say that the detector now tells us that it is left polarized. If we now look at our table, we can see that the photon must have gone through slit 1. And to complete our table, of course we can do the same thing when the B photon is determined to be X polarized. So now, finally, with this setup, we can determine through which slit each photon goes. It's crucial to remember that the information from the B side is absolutely necessary to determine through which slit the photons go. We need the information from both detectors. Let's rerun the entire experiment with this new setup. Remember, all we did is put the red and green quarter wave plates there. We'll run the experiment again and move the A detector again, counting the incoming photons and writing the results down in a graph, just like I showed you previously. This time, something interesting happens. Instead of getting a graph with an interference pattern like this, we get a graph like this. The interference pattern has disappeared. The outcome of the experiment has changed simply because we're observing it. At this point, you might be very skeptical though. You might say, well, of course the outcome has changed. We changed something in the experiment. We put the red and green crystal in front of the slits. You might think that the two crystals affect the particles in a way that makes the interference pattern disappear. However, this is not the case. Let me show you. We're now going to introduce another device into the experiment, a polarizer. A polarizer is an optical filter, not unlike the 3D glasses you use in a movie theater. However, the polarizer we use here will make a photon that passes through unpolarized, which means that it completely erases all polarization from the photon. We're going to put this polarizer in front of the detector in the B direction. As you can see, we're not going to change anything at all in the setup of the A direction. When the B photon now arrives at the detector, all we can say is the time it arrived, but not which polarization it had. That means we also can't tell which polarization the A photon had when it left the BBO crystal. When it arrives at the detector, maybe it is right polarized. But now, if we look at our table, we have a problem. We can't determine through which slit it went anymore, since there are now multiple possibilities. Because we erased the information from the B side, we're unable to observe through which slit each photon goes. Now, we rerun the experiment, and the outcome is really surprising. The interference pattern reappears. Adding the polarizer changed the outcome of the experiment, even though there is no way it could have interfered with the particles in the A direction. It simply changed the outcome because we're no longer able to observe through which slit each particle went. Now, how can we interpret this result? You might conclude that there must be some kind of unknown force or communication between the two particles. One photon must warn the other in some way that's still unknown to us as it goes through the detector that is being observed. However, we can still change the experiment slightly to even exclude that possibility. Imagine we put the A detector very close to the BBO crystal and the B detector and the polarizer very, very far away from it. Now we know for sure that the photon at the A side will go through the slit long before the B particle even gets close to the polarizer or detector. There's no way that the A particle's trajectory could somehow be changed by some secret communication from the B particle. However, the experiment still behaves exactly like before. Observing through which slit each particle goes changes the outcome of the experiment. When the polarizer is there, the interference pattern will appear. When it's gone, it will vanish. This is all very strange, and there are many different interpretations of this experiment. You can find some links in the video description. Let me know in the comments what you think, and thanks for watching.